Hi everyone, my name is Alex, I'm an engineer and my passion is with design, development and prototype production of all sorts of engineering solutions. In this video I would like to walk you through the basic setup of this here, my 40-ton force and 1.2 meter span or 4-foot span if you want prototype press brake. Also I will say a few words about the insert tooling which I use. And finally, I will show you how to use this press brake for actual bending work. So let's take a look. I designed and built this new press brake as a follow-up model to my first press brake. Among my YouTube videos you can find one called Pumping Iron, which shows how I managed to machine these here sidewalls with my, for this kind of work, very limited equipment. But anyway, my first press brake I built just as a quick and dirty project in order to get some urgent and intricate bending work done. This new one, however, differs from my first one in some key features. Of course, it is more powerful, has more span and is not so high. But this is not primary. What's much more important for me is that it provides way more clearance around the frame here and around the girders up here and down here, and that it has open sides here. Believe it or not, this means freedom in the bending world. Kind of like unlimited travel on your mill or lathe, which neither one of us has. Basically, this press brake uses a single hydraulic cylinder in the back here, which operates a bell crank or lever in general up here. This lever's movement then is coupled to these radius links up here, which compensate the horizontal movement, and from there to the upper girder. And this upper girder is held to the frame with these here roller guides. Now there is a lot of thought behind the design of this upper bell crank arrangement here, particularly in terms of rigidity. You see, what distinguishes a good from a bad press brake design is primarily how its bending gap, here, deteriorates elastically while the press brake is worked. This is particularly important in cases when you cannot work your workpiece in the center of the press brake, but rather have to work on the outsides. This may be necessary because of workpiece collision issues with the frame or with the girders. And believe it or not, with my workpieces, this happens frequently. I test the aforementioned bending gap deterioration with this setup here. What I do is, I set up two indicators on the very end of the girders. Then I apply certain press forces on an eccentrically placed cushion insert in order to provoke bending gap deterioration. The difference of the indicator readings now quantifies how good or bad the press brake is in terms of this rigidity. Also, it lets you compare the one press brake to another press brake. Paramount in terms of bending gap precision are these three bearing points, of course. I designed these so they can be preloaded in order to get rid of any bearing play. These two inner ones, for example, are slotted and can be adjusted by means of these two fine thread bolts here. And the main pivot up here is preloaded by means of a tapered and slotted bushing, which is adjusted by this central bolt. Also at these links here, we have precision lapped both bolt and bore and have a slight press fit here on the outside, in order to avoid bearing play as much as possible. Also paramount for rigidity, of course, is proper sizing of these bearings. But now let's talk about the basic setup. Upper and lower girders here, they have scraped surfaces where they contact the insert tooling. That is up here in the slot and below the tool rail here. Now, these scraped surfaces must be set parallel to each other. And this is accomplished on this press brake design here with these two fine thread studs down in the basement, so to speak. Here is a shot to show you how I test this. What I do is I use a scraped base for my dial indicator holder and traverse the girder span from end to end, like so. So this is a 10 micron per division indicator, and let's see about parallelism between upper and lower tool holders along the whole span of the press brake, which is 120 centimeters or approximately 4 foot. When set parallel, these bolts here are torqued down thoroughly. Then I apply the full press force, let the two studs settle a bit, and then I test again. Usually the one or the other bolt settles for a few microns and has to be readjusted one time, but then it should be fine. Next I install the lower insert tool rail here. And this rail must sit in place symmetrically in this direction with respect to the upper insert tooling. This is adjusted with these two pairs of set points here. These two. The next shot shows you how I test this adjustment. And I test this with the aid of a scraped base here, which is down here. And I push the base against this side of the rail and memorize the value. Then I turn it around and push it towards the other side of the rail. And then I have to adjust for half the difference. This looks good enough for me. Yeah, good enough. Next we conduct the same adjustment on the other side of the press brake, and then we come back to this side again to check if nothing has shifted. And then we should be fine. However, I must mention that this adjustment here, this concentricity adjustment, is not as critical as the adjustment of vertical gap. The error in vertical gap impacts way stronger on the bending result than an error in concentricity here. And by this I mean, if the errors are too large, then we get a notable difference in bending angle over the length of the workpiece. Well, this is basically all that is necessary adjustment-wise on this press brake. That is, of course, with the exception of the pivot point preloading adjustment, which I spare here for the sake of simplicity. Well, let's take a quick look at the insert tooling I use. This here is some of what modestly accumulated over the years. In general, the steel insert tools like these here and these I machined from preheat treated tool steel, alloy number 12312. I'm sorry, I don't have in my head an imperial equivalent material for this, but I'm sure you guys will be able to look it up if you need it. After machining, I polished the contact points in order to keep the workpiece scratching to a minimum. My lower steel insert toolings, I hope the focus is good, they are fairly simple. What I do is I machine an array of slots into them in order to clear the workpiece, and then I round over the contact points up here with a round over bit, and then I polish them. I have wide as well as narrow inserts, and the narrow ones are much more sensitive to setup errors and girder movement, but they are necessary in cases with workpieces with narrow flanges and such. Also, I have lower insert tooling out of Delrin for much more scratch sensitive work, like this one here. I bought these ones from a company in Germany, but for the love of God, I cannot understand why they machine them with a sharp corner down here, even though this is not necessary and limits the maximum force for these inserts. But anyway. And also for extremely scratch sensitive work, I have these here polyurethane cushion type inserts. Now these polyurethane inserts, they require that the lower insert holder is rounded over here like so in order to avoid damaging them. And they work like so. And you see, for them it doesn't matter if the upper inserts end within the cushion or not. The cushion doesn't get damaged by the upper inserts. They are really nice in terms of scratch prevention. You see, there are no markings whatsoever on the lower side. However, they require quite some additional press force in addition to the bending force of the workpieces, which may be necessary to consider if you're borderline with the press force and with the width and thickness of your part. Another problem about these cushion type inserts is that they don't behave perfectly repeatable. Let me try to show you this. Here I contact at 0. And here I contact at 0.3 or 0.35. And this difference needs to creep back, and it usually requires about a few minutes up to an hour or so until this is done, depending on the temperature, of course. And this may be unimportant in case of serial work where you have constant time steps between your sequential workpieces. However, it matters a lot in prototype production because you have to rebend and rebend until you find the proper angle. For the upper insert tooling, I only use tool steel, the same one as I mentioned before. It's pre-heat treated tool steel, material number 1.2312. And as a remnant from my first press brake, I have various radius caps like this one here, or like this one, which can be slid onto my standard radius inserts like this one here. This works fine, except on the wider inserts on which they tend to jam a bit. If you ask me now, I would instead make dedicated upper insert tools for each radius, just for simplicity and ease of work. But back in the day I had to consider material cost much more than luckily I have to today. On this press brake I chose to use a holding system with an angled slot, as you can see here. And the system is established, I think, with some press brake manufacturer. However, I don't recall which one. The slot is grabbed by set screws, like so. and the set screws, they touch the slot only on this upper surface here. They thereby push the insert toward the rear and toward the upper scraped surfaces. And on the upper scraped surface, the insert transmits the bending load into the upper girder. This system is straightforward, easy to make and intuitive to use. Also, if you have installed some narrow inserts, like so, with this system you run little danger of accidentally loosening a narrow insert, which then may fall down and get damaged on its polished surface, a problem I had on my former press brake. If you are still with me and not yet bored to death, let's take a look at some bending work with this machine. The part I work on here is a laser cut engine mount out of 4mm thick medium strength carbon steel. If you look closely, you may be able to see that my upper insert tooling carries one of the aforementioned radius caps to ensure the required 4mm bending radius. First, I sneak up on 0, but leave a gap of roughly 100 microns. Since no sheet is perfectly flat, this slightly clamps it between upper and lower inserts and lets you set the bending line conveniently. Since I'm not a big fan of backrests for the kind of parts I make, I set the bending line by means of this acrylic glass piece here. Its thickness plus half the upper insert's thickness add up to 10 mm. This means beforehand on the sheet I placed two marks 10 mm next to the bending line mark. And these marks here I set to coincide with the glass piece. Here I set my protractor to the required angle to eyeball the first bend. I do this because for this material, bending radius and lower insert combination, I didn't bother to make an angle depth lookup table like the one on the paper to the right, which is for other, more frequent combinations. Wow, Alex, are you suicidal or why do you put your head there? Relax guys, this press has limited stroke. There is no danger to break open my head. Here I memorized the depth, which is necessary for the following correction step. Now checking the angle and correcting. With the lower insert tooling used here, roughly for every 100 microns depth you get 1 degree additional bending angle. Here I'm feeling how to place the part symmetrically while I sneak up on it. Checking again. Still missing half a degree. Checking again, and this time it's fine. The second bend is easier because the target angle is the same, which means I can go to the same depth as before. Checking. And I have to correct one time because this is cold rolled sheet, which has slightly different strength as you deviate from the previous in-plane direction. But correction steps are typical also on most modern or very expensive computer-controlled press brakes. This is material behavior which the press cannot know exactly. And that's it, easy peasy. Well guys, as always, thank you very much for your interest in this video. I hope of its content you find the one or the other thing useful. All the best and thank you!